Hi, I'm Sanjaban Chaudhary, a technical lead in the motion planning team at Aurora. I work on theory and data driven methods for imitation learning, forecasting, and decision making. In the self driving industry, it's common to see a diagram like this explaining how an AV makes decisions. This is the traditional cascaded approach to forecasting. First, we perceive where all the actors are, then we forecast where they'll be in the future, and finally, we make decisions based on those forecasts. While this may sound reasonable, it doesn't actually capture how the world works. Let me show you. Here's an urban example of the AV taking an unprotected left turn at an intersection with vehicles, bicyclists, and pedestrians. There's a lot going on here, so let's break it down. We can see that the Aurora Driver's actions depends on what other actors in the scene are doing. We need to yield for the vehicle turning right, as well as the pedestrians crossing the intersection. Moreover, the oncoming car is also waiting on the AV to determine when it can attempt its own unprotected left. So effectively, this is a joint interaction where the forecast for this actor depends on what the AV does. Furthermore, other actors in the scene also interact with each other, and we need to take into account how those interactions could affect the AV's options. Here, the vehicle turning right is waiting for pedestrians to cross before making its turn. So our left turn depends on that car's right turn, which depends on how those pedestrians move. Driving is full of complex interactions like these. The way you behave on the road affect the way vehicles and other road actors around you behave. At Aurora, we've built our system from the ground up to reason about all of these interactions. Instead of the traditional cascaded approach, where the AV plans its movement after forecasting the movement of other actors, we take an interleaved approach to forecasting, which allows the Aurora Driver to reason explicitly about its decisions in context of how other actors will respond. In complex interactions like this one, the Aurora Driver reasons about the interactions among all of the actors in the vicinity. We can picture the way it works by imagining each actor as a node in a graph. The edges of this graph tell us relationships like, is actor A yielding to actor B? Looking closely at these relationships, the system can narrow things down to a subset of actors that directly affect AV's behavior. We can then abstract away the rest of the scene and only look at the graph of these relevant interactions. Our geometric transformer net inference engine, leveraging state-of-the-art graph neural networks, enables the Aurora Driver to jointly reason over the graph of interactions between actor nodes trained from expert human driving data. This results in a set of self-consistent forecasts for all actors in the scene that account for the actions of the AV. By having this rich understanding of how the world may play out for different decisions, the Aurora Driver is able to make more informed choices in complex scenarios like this one. Moreover, the graph structure naturally generalizes to different scenarios. Let's play this out on the original scenario. We see that by reasoning about different interactions, the Aurora Driver is able to confidently navigate this complicated intersection. Our interleaved forecasting approach allows the Aurora Driver to exhibit predictable human-like behavior, and the more data we collect, the better the system gets. It also ensures safe driving in potentially critical situations like the one shown here, where a cyclist pops out from behind an oncoming vehicle. The Aurora Driver must quickly perceive it, incorporate it into its forecasts, and create a new plan to execute this turn safely. Okay, I've shown why this matters in urban settings, but all of this transfers to highway driving as well. Consider this common scenario on the highway where we are negotiating a merge with other actors and trying to decide how to adjust our speed to find an open slot within a stream of traffic. Here too, we apply our learned geometric transformer net inference engine. As we all know, merging is inherently an interactive process, where the behavior of other actors depends on what you do. Although it looks like there isn't room between vehicles currently, the Aurora Driver explicitly reasons about potential effects of its actions on the other actors. Based on this interactive reasoning, the AV chooses to slow down, merge behind the first two vehicles, while the third vehicle makes room and merges in behind as expected. We again see how interleaved forecasting allows the Aurora Driver to make better decisions in interactive scenarios, even at high speeds with an 80,000-pound truck. Learned interleaved forecasting also enables us to predict goals of other actors. We used a learned attention model to generate a matrix of probabilities for every actor on every lane. But sometimes people do unexpected things, like this actor cutting across a solid white line to merge in. Watch how the lane probabilities for this actor switch from merge lane to the AV lane as the actor cuts in. The learned attention model quickly detects that this actor is cutting in, and we slow down as needed. Even in complex scenarios, the Aurora Driver is constantly computing a huge matrix of actor attentions. We saw that both urban and highway driving are full of interactions where you need to reason about how other actors will respond to your decisions. These interactions are often subtle, and hand-tuning things only get you so far. That is why we've built the Aurora Driver using state-of-the-art foundational tech like the geometric transformer net, trained from expert human driver data to reason about interactions and exhibit human-like, predictable, and interpretable behavior on the road. Thank you for your time. We hope you enjoyed learning about forecasting and decision making at Aurora.